Hello guys, and welcome to my video. So today we're going to be focusing on the February-March 2016 question paper 2 for physics, and the question paper is 1 hour 15 minutes long, and we're going to be explaining in depth how some of the questions were supposed to be worked out, and at the end I'm going to share some valuable tips on how you can tackle physics questions. And if you find anything interesting and you really want to learn more, please do like and subscribe so that this content can be able to reach more people. Okay, let's begin. The speed v of a transverse wave is given by this following expression, where t is the tension and L is the length and m is the mass. An experiment is performed to determine the speed v of the wave. The measurements are as follows. State the appropriate instrument to measure L. So what you need to do is you need to ask yourself, how big is L, so we can determine how much we need to measure. So the length is essentially 126 meters. 126 meters, guys. A normal meter ruler basically has something like 100 meters, right? A normal meter rule is a length of 100 meters, right? So if you want to measure 126, yeah, you could try. I mean, put 1 meter rule, then put it again to measure that 26 centimeters, but it's pretty difficult. My advice would be for you to use a tape measure. That would be much easier and much quicker. Using the data in Fig 1.1, calculate the speed v. Okay, so this is just a matter of substitution, guys. You're getting marks just for substituting, right? Physics has never been so grateful. So we have v is equivalent to the square root of t times L divided by m. Okay, t times L divided by m. So it's going to be the square root of, our t is 1.8, our length is 126 times 10 to the power of -2, to put it in meters, divided by our mass, which is 5.1 over 1000. Okay, so this is going to give you a value of v of around 21.08 80507. So this is essentially 21.1, right? So our value of v would just be 21.1. What are the marks? Where are you getting the marks from, guys? If you just give them an answer, they give you a mark. If you give them a working, they give you another mark. So basically, this is how you are supposed to think of this particular question. Move on, question number 2. Use your answer in BI and the data in Fig 1.1 to determine the value of v, and with its absolute uncertainty, to an appropriate number of significant figures. Why are they saying this? Why are they saying to an appropriate number of significant figures, you might ask? Well, the number of significant figures of an uncertainty is always 1SF. That's a law. Remember, whenever you're given an absolute uncertainty, try to express it to 1SF. Hence, your value of v will sort of adapt to that uncertainty. So if you go here, we basically have an equation, right? And if you've done uncertainties, if you haven't, we'll explain it. So basically, v is equal to the square root of t times L divided by m, right? So basically, how we do this is that if you see, this can basically be expressed as t times L divided by m to the power of 1/2, right? Because the square root is to the power of 1/2. So the rule is the percentage uncertainty in v will be equal to, you just add all the percentage uncertainties of everything, or all the fractional uncertainties of everything. Okay, so it will be the fractional uncertainty in t plus the fractional uncertainty in L plus the fractional uncertainty in m. And then if you see a power, you multiply whatever variables were included in that power by the power, right? So here with all these fractional uncertainties, and our power was 1/2, so we just multiply by 1/2. So that's sort of how you think of fractional uncertainty. So the fractional uncertainty in t was 5%, L 1%, M 2%. So it's 5 plus 1 plus 2 times 1/2, and that's going to give you 8, and that's 8 times 1/2, that's going to give you 4%, right? So it means that the fractional uncertainty will be 4%. So for you to find the uncertainty in V, right, the variable that you actually want, it is now going to be equivalent to, if you look at this, it's now going to be equivalent to 4 over 100 multiplied by the value of V itself, which is 21.1. That's going to give you about 0.8435. Remember my rule, I always say it to 1 SF, so this is going to be 0.8, right? So 0.8, and the value of V would respond to that uncertainty, so the value of V would just be 21.1, right? Question 2, define acceleration. This is a recall question. You should just be able to sort of recall and get this mark. So basically, acceleration is the rate of change of velocity. That's basically acceleration, right? Or someone might say it is the change in velocity divided by the time taken, right? But you must never ever, I repeat, you must never say the rate of change of velocity per unit time, because if you do that, you are repeating time twice. You said the rate one, then you're now saying per unit time, so you're repeating the time aspect 2 times, so that would be incorrect. Moving on to B, a ball is kicked from a horizontal ground. So we have a kid playing soccer, then they kick a ball and then it hits a wall. Maybe it's a neighbor's wall or something like that. The neighbor is going to be angry, I suppose. So the ball is going to follow a certain path, right? And then it's going to arrive and follow a certain trajectory. The resultant distance between the initial position and the base of that wall is 24 meters. So the child was 24 meters away from the wall when they were doing this. The ball is kicked with an initial velocity V at an angle 28 degrees. The ball hits the top of the wall at 1.5. Air resistance may be assumed to be negligible. Calculate the initial horizontal component Vx. Now, for projectile motion, it is very important for you to take note of the following. The horizontal component, right? The horizontal component in this direction, Vx, always remains constant. It always remains constant, right? It never changes. And then you know that the distance from your kinematic equation, the distance r, will be equal to the velocity in the x times the time that will be taken to move that distance r, which is the range, because you know that the range is distance is p times time, right? So it means that Vx will be equal to r divided by the time t. Your value of r is 24. Your value of t is 1.5. So Vx will essentially be 16 meters per second, right? So essentially it's very, very important for you to be thinking of that. So what are your marks? Your marks are just for you doing all of this calculation, right? All of that calculation will just earn you 1 mark. Show that the initial vertical component Vy of the ball is 8.5. Okay, so if you were to go here, we have V, which is acting in this direction. But if you're going to apply certain trick, right? Physics is application of tricks. This is the vertical. Okay, this is your vertical, and then this is your horizontal, like so, right? So you can see sort of have a little triangle situation going on here. We have 28 degrees, and we know that this is 16, right? And then we basically know that this is our adjacent, right? This is our angle theta, this is our adjacent, and then we know that this is our opposite, right? Why is it our opposite? Because we also have it in this direction, and it's opposite to this angle of 28 degrees, right? So if you were going to apply trig identities, we know that tan theta will be equal to opposite divided by adjacent, right? This is just something that you should have on your arsenal, flexible in using trig identities, so, or trig relationships. So tan theta will be equal to, your opposite is Vy, your adjacent is Vx, therefore Vy will be equal to Vx tan of theta. Your Vx is 16, tan of 28, and that will basically give you 8.507350907. So that's essentially 8.5 meters per second. Calculate the time taken for the ball to reach its maximum height above the ground. So the ball is going to rise and rise and rise and rise, and then it's going to reach this specific point, right? This specific point is essentially the maximum height, and we just want to find the time taken for it to reach the maximum height. So you see that if your ball is here, right, if your ball is here on this maximum height, you can agree that the only velocity that will be present will be in this direction, right? We can't resolve it because if it's here, your velocity will be in this direction, so it will have a vertical and then it will have a horizontal. But when it's at the top, the only thing that's there is the horizontal. So it means that the vertical of Vy will be equal to 0 when you are at the top, and that's very important, right? We can apply something that was created by a very famous physicist, Sir Isaac Newton. Thank you very much, Sir Isaac Newton, for giving us the Newton laws of motion. So what are we given and what do we need to find out? This is the easiest way to work out Newton's laws of motion, right? So we want to find the time that will be taken. That is what we don't know, okay? But I know that the final velocity in the y direction will be equal to 0, and I know that the initial velocity in the y direction will be equal to 8.5, because that is what I've calculated above. Then I know that the value of g, okay, the value of g is going to be 9.81, because since air resistance is negligible, the only force acting on this whole system is actually the weight, and we know that the weight causes an acceleration of 9.81. So I have v, okay, I have v, I have u, I have g, and I have t. What equation can I create? You've guessed it. V y will be equal to uy minus gt, right, plus gt. But we know that g will be acting down, okay, because g is the weight which acts down. So basically this can just be a negative because g will be negative acting down. But this is 0, so it means that g times t will be equal to uy. So your t will essentially be equal to your initial velocity in the y divided by the value of g. Initial velocity in the y is 8.5. Your value of g is 9.81. So this will essentially give you 0.8672069,317. So to yourself, this will be 0.87. Okay, so this is something that I just had to think of, that we have a specific equation that can relate all of these three variables, because t, acceleration, is equal to v minus u divided by t. So vy will be equal to uy minus gt, negative because g will be acting down. So using that equation, you can therefore be able to find this time. IV. The ball is kicked at a time t is equals to 0. So very important for you to pay attention to all of this. Sketch the variation of the vertical component of the velocity Vy until it hits the wall. It may be assumed that velocity is positive when it is in the upward direction. So if you look at this, we are starting with a velocity of 8.5 over here, right? And here the velocity is 0, right, at the top. Then here we're going to end our journey with again a specific velocity. So I can find that velocity just to be fancy, right? I can basically find the velocity that was acting on that specific direction, you know, just to be fancy. So how do I find that velocity? We know that we have our famous equation. Vy is equal to uy minus gt, right? So my Vy will be equal to 8.5 minus 9.81. The time taken is 1.5. So that's basically negative 6.215, right? So basically I've just found, if you look at it, I've just found the velocity that will be present as it will be moving down, just negative 6.2, right, essentially. So here we have negative 6.2, right? Here we have 0, and then here we have 8.5. So we can sort of plot a graph, right? Because we have coordinates, we have all these coordinates, right? And then what we can essentially do is now determine, is the graph going to be a straight line? Of course it is, because acceleration is constant. And if you know velocity time graphs, you essentially have to know that the gradient for velocity time graph symbolizes acceleration. So what it means is that if the gradient is constant, therefore the acceleration has to be constant as well. Or if the acceleration is constant, the gradient has to remain the same. So if you look at this, what coordinates do we have? This is sort of the easy way out of this. So if you're looking at this, ask yourself, what coordinates are you given? Right? The first coordinate, like you have said, when x is 0, when the time is 0, our velocity is 8.5. Sort of the first coordinate that we have, right? Number 2, when x is 0.87, that is when the time is at 0.87, that is where we have a velocity of 0. Then number 3, when you are done and our velocity is 1.5, our time, right, will therefore be our final velocity will be negative 6.2, like I've calculated. So basically these are my group of coordinates. These guys are going to help me draw my graph, and then I also know that I'm going to have a constant gradient, right? And what this tells me is that I'm essentially going to have a straight line. Okay, I hope that makes sense. So we have a specific gradient with specific coordinates, and then a constant gradient will essentially mean that we're going to have a straight line. So let's start plotting. To begin with, we have 0 and 8.5. So we have 0 here, right? So it means that if you look at this, each line symbolizes 0.5. So we have 1, 2, 3, 4, 5, right? So if you're here, this would be 6, this would be 7, this would be 8, and then this would be 8.5. So this is our first coordinate. Okay, and then if you look at 0.87 and 0, so if you're here, this is 0, this is 0.82, 84, 86, 87. So we're essentially going to have our coordinate here. Then if you look at the end, we have 1.5 and negative 6.2. Okay, so essentially we're going to have 1.4, right? 1.42, 44, 46, 48, 1.5 is here. Okay, then if you go down that line, this is 5, right? So this is 6, 6.5. So basically it would be somewhere here, right? So basically these are sort of the relationships that we have established. Our job is just now to draw a straight line. So we are starting here, our line passes through here, then it goes through to that point, right, like so. So this is essentially how we're supposed to draw it, a straight line. Why? Because the gradient has to be constant and it has to pass through this point, and it must not exceed 1.5, because 1.5 we're done. right? So what were your marks? Your marks were just your M1 mark for this entire graph, right? Just showing us that this graph is a straight line that is from positive to negative at 1.5. And then because the line started here, very accuracy mark A1, your line started here, then it crossed at this point, then it did not go beyond this. So here I'm obviously a little bit off because it's going a little bit beyond, but yours shouldn't go beyond, right? So it should just end at this particular point. And it's a straight line. It's not, I don't know, it's not a line like so or a line like so, I don't know, right? It has to be a straight line because the gradient has to be constant. Using the information, determine the maximum height that has been traveled. So I basically know that my displacement is equivalent to my area under the graph. In my area under the graph, this is a triangle, so it's going to be half base times height. Then the maximum height is basically when I've reached this point, right? This point is my maximum height, right? So it essentially signals to me as a physicist that all of this area A is the distance that I've traveled to reach that maximum height. And if you look at this, our base, this is our base, and then this is our height, so half base times height. Our base will be 0.87 times our height, which is 8.5, and this is essentially going to give me 3.6975 and so forth. To 2SF, I'm gonna get 3.7 meters. So 2 marks. Where are my marks coming from? I need my marks, guys. The first mark comes from you just showing me a specific method. Then the other mark comes from you giving us an answer. The maximum gravitational potential energy of the ball above the ground is 22. Calculate the mass of the ball. So the ball has been raised and has reached a specific maximum height, and we're told that the gravitational potential energy at that maximum height is 22. So we just want to calculate the mass of the ball. What do we know? Start with what you know. You know that your GPE is equivalent to mgh. So your mass m will be equal to GPE divided by g times h. Right? Your G is 22. Your GPE is 22. Your G is 9.81. Your H is 3.7. Punch this on a calculator, 0.6061106. So essentially, our mass will be 0.61 kgs. My marks, just I give them an answer, they give me a mark. I give them a working, they give me another mark. D. A ball of greater mass. So we had one ball, now we have a ball with a greater mass that is kicked, but there's a catch at the same velocity. Send and explain the variation, if any, of the increased mass on the maximum height reached by the ball. Okay, so essentially what we want to find is, can mass affect the maximum height? Can a change in mass affect the maximum height? Right, so we know that for all objects, regardless of their mass, right, they travel at the same acceleration in a vacuum, right? We basically know that acceleration is constant, right? If you remember the famous saying that a feather and an elephant will fall at the same rate when they're placed in a vacuum. Yeah, it's that crazy, right? When placed in a vacuum, an elephant and a feather will actually fall at the same rate and will reach the ground at the same time. So that's basically, right, the same thinking that we're using here, is that the mass really doesn't matter. And if the mass doesn't matter, because the acceleration of free fall is unchanged or does not depend on a mass, so if you're kicking it with the same velocity and then the acceleration is going to be the same, it essentially means that the height that you're going to reach is not going to change, right? Because the acceleration is the same and you're kicking it with the same velocity, there's no way that the height will change. Because what are the equations that we know for calculating height? V squared is equal to u squared plus 2as. We know that the acceleration is the same, v is the same, u squared is the same, so s shouldn't change. we also know that S is equal to UT plus half AT squared. The time will be the same, U will be the same, so S therefore has to be the same. So how do we put this in words? Well, we can just say the acceleration of free fall is unchanged. Okay, so basically the acceleration of free fall is unchanged and is not dependent on mass, right? Hence the maximum height will not change. Okay, so hence the maximum height will not change. So that's essentially what you need to be thinking of. Moving on. 3a, state what is meant by work done. Recall question and you get a mark, right? Work done is basically the product of the force applied, right, and the distance moved in the direction of the force. Right? So if you have a certain force that is applied on an object and that object moves in a specific direction, that is essentially work done. You have done work on the object. So if a force is applied, certain distance is moved, work is done. Elastic potential energy, this is the energy stored. Emphasis on stored, right? This is the energy stored. Big emphasis on the word stored in an object, right, due to its state of being, extended, right, or compressed. It really depends on a lot of things. Extended, compressed, or just essentially change of shape, right? Or essentially just change of shape, right? So basically that's elastic potential energy. How much energy is stored in an object due to its state of being extended, compressed, or just having its shape changed. A body of mass 0.4 slides, so this body is going to slide, right, with a constant speed of 0.30 meters per second along a horizontal surface. Along the horizontal surface with a constant speed, the block hits a spring, so it hits the spring and then it decelerates, right? So after some time, our block is sort of gonna hit the spring. So it was once here, right? But after some time, our block is going to be here, right? And when our block is going to be here, it's gonna hit the spring, then it's going to decelerate, right? So just want to calculate the initial kinetic energy of the ball. What do we know? We know that kinetic energy is essentially 1/2 mv squared. So always ask yourself, what is your initial mass? Does it change? Of course it doesn't, right? 0.40. What is our initial velocity? 0.30. We can square that. So it means that our initial kinetic energy will be 0.018. If you want to be fancy, put it in standard form, right? Show them that you also have efficient math skills, right? Like so. So we have 1.8 times 10 to the power of -2. 1.2. The variation of the compression of the spring with the force F applied is as shown. Use your answer in BI, which is the kinetic energy, to determine the maximum force F max exerted by the block. So I want you to see something here. We've been told that it slides along this surface, right? And then it sort of decelerates. So it means that if we had the initial kinetic energy that we had, it's that kinetic energy that is used to sort of compress the spring. So it means that the work done, or the elastic energy stored in the object, should be equal to the initial kinetic energy that we had, right? So we can write that down. So it means that the change, right, in kinetic energy will essentially be equal to the work, right, done on spring, or if you want to be fancy, the change in elastic potential energy. Okay, so the change in kinetic energy, as we've calculated from above, is 1.8 times 10 to the power of -2. And how would you find the work done? It is essentially my base times my height, which is half. My base is F max. Then my height here is 8 centimeters. Okay, so it means that if I go here, my change in kinetic energy would just be equal to 1/2 F max times x, which is 8 times 10 to the power of -2. So x, not x is in Twitter, guys, right? So it's x half fmx. All right, so it means that my f max will be equal to 1.8 times 10 to the power of -2 times 2 divided by 8 times 10 to the power of -2. So my f max will be 0.45 newtons. So 0.45. Okay, calculate the maximum deceleration of the block. Okay, I have the word deceleration. How do I find that? Well, if you know it, F max is sort of equal to our resultant force, because it's sort of the force that is applied by the block. So it's sort of the force that is causing the block to actually decelerate. Because think of it, when the block is applying here, it's applying a certain force on the spring, and the spring is going to apply the exact same force on the block. So that force is what's going to cause that block to actually come to a standstill, and that's the only force acting in this scenario. So we know that F max therefore has to be equal to your mass times your acceleration. In this case, it's your deceleration, because F max will be negative in the opposite direction, right? But we don't care about signs. So it means that because deceleration caters for that, D sort of stands for a negative, right? So it means that my acceleration will be equal to my F max divided by my mass M. My F max is 0.45, and then my mass M is actually 0.40. So it means that if I compute this, I'm going to get, something like 1.1025 and all that stuff, right? So it means that my deceleration will just be 1.1 meters. So 1.1 meters. Okay. Stand and explain whether the block is in equilibrium. Whoa, wait. What does the word equilibrium means? There are two cases that you need to learn in AS level physics. And once you've understood this, you're done. You're a guru in equilibrium situations, right? You need to know two things. Number one, for a system to be in equilibrium, the resultant force, right, must be 0. Okay? The resultant force must be 0. And you must know that for also to be in equilibrium, the second thing, the resultant torque must also be 0. Right, so those are my two scenarios. The resultant force must be 0, and then the resultant torque must be 0. If you understand this, you're pretty much done with equilibrium situations in A-level physics. Okay, they really come a lot, and just by understanding these two concepts, you're pretty much done. So we just want to find if it's in equilibrium before it hits the spring, is the resultant force 0 or is the resultant torque 0? We can't talk of torque, guys. It's not going to rotate in any way whatsoever, so we can only talk of the resultant force. So before it was moving at a peaceful constant speed of 0.30. If the speed is constant, guys, it means that there is no resultant force whatsoever, because if there was supposed to be a resultant force, there should be an acceleration or a deceleration for that matter. So it means that since, okay, this is just you saying it and getting your marks, right? Since we have a constant velocity, okay, since we have that constant velocity, the resultant force is 0. Hence, the block is in equilibrium. Okay, when the speed becomes 0, in this case, it's decelerating, right? When the speed is becoming 0, the block is actually decelerating, right? Decelerating. Hence, the resultant force cannot be 0. Hence, the resultant force is not 0. So the block is in equilibrium. Right, so those are the two things that you just had to take care of. Is the resultant force 0? In this case, we can't talk of torque, we can only talk of the resultant force. E. The energy stored in the spring is given by this relationship, where K is the spring constant, X is the compression, right? The mass M, so compression, as the spring is compressed, that compression will just be X. The difference between the final length and the initial length that you had. The mass M of the block is now varied. So we have a bigger block, a smaller block, a bigger block, a smaller block. The initial speed of the block remains constant, and the spring continues to obey Hooke's law. Sketch the variation of the maximum compression X naught with the spring M. So we have already said that EK will be equal to the energy that will be stored, right? So we have said that 1/2 mv squared should be equal to 1/2 kx squared. But guys, v is constant because it's the initial velocity. X is constant because we show that the initial speed remains constant. So that's the kinetic energy that we once had, right? So X is also constant. Sorry, K, which is, and the K, the spring constant, is also constant, right? So it means that we have a relationship between M being directly proportional to X squared. So I'm going to teach you a trick, right? We're going to do these tricks a lot that helps you sketch any graph that you see on Earth. That trick is make a relationship. And once you have a relationship, deduce what that graph is going to be. So in this case, I started by saying my kinetic energy will be equal to my value of E, and I created this equation. This is a relationship, guys, that relates EK and E, right? And then I identified what was constant, two things which are constant. Then I had the resultant relationship between M and X. So that's how you do this relationship. So this is a graph that you need to plot, okay? But X is on the y-axis and M is on the x-axis. So you just have to make sure that that is what's happening. So it means that if you put X on the y-axis, X will be directly proportional to the square root of M. So this is a graph of Y is equal to the square root of X. Essentially, that's the graph that we need to plot. And do you know this graph? You might not. So I'm not going to assume that you do. So we're going to take a little detour, okay, and do a little math lesson, right? Just for three or 4 minutes or so. 2 minutes actually. We can finish it fast. So we're going to do a little math lesson, right? So welcome to Graphs 101. right? Let's draw some graphs. The first scenario that we're going to have is when we have a graph of y directly proportional to x. So this can be y is equals to kx. The second scenario is when we have a graph of y inversely proportional to 1 over x. This can be a graph of y is equals to k over x, where k is just any constant, right? The third scenario is when we have a graph of y directly proportional to x squared. So y will be equal to kx squared. You probably drew a graph of this in math, the graph of x squared, right? And then number 3, we're going to have when y is proportional to the square root of x. So y will be equal to k, the square root of x. K can be 1 as well, right? So we're going to draw specific graphs, right? And then we're going to sort of make relationships. Y is equals to x, which is just a straight line which passes through the origin. So if you ever make a relationship and you discover that y and x are directly proportional, just draw a straight line, right? And if you find that y and x are inversely proportional, what are you going to do? You're going to draw this line like so. This is the graph that shows inverse proportionality. If you ever find that y is directly proportional to x squared in any calculation, you make y the variable that is on the y-axis, right? And then you have x, the variable that is on the x-axis. If you ever find this, you're going to draw a graph like this, right? So it's a graph with increasing gradient, so sort of like a little curve, right? Like so. I don't know, right? A curve. Okay, something like that, right? So that's a graph that you're going to draw whenever you see that y is directly proportional to x squared, because it's going to be a graph like this, right? Y is equal to x squared. So we just take the positive part. That's what we're mainly interested in as physicists. And then the last relationship is when you see y is equal to the square root of x. It's going to be a graph like so, right? Like so. There's going to be a graph of decreasing gradient, right? Your gradient is sort of going to be decreasing as we will be sort of moving along the graph. So these are some of the 4 scenarios that you see. You can probably see other graphs, but if you have a very strong mathematical background, you make a relationship, then you just know automatically this is the graph that I need to draw. So in this case, we just read here, x is equal to square root of m. So tell me, guys, between graph 1, 2, 3, and 4, which one is it, right? Between graph 1, 2, 3, and 4, which one is this graph? You can tell me, right? It means that since we have y with x and the square root of x, right, the square root of m is going to be this graph. So essentially that's the graph that we need to draw. Recall, right? So if you make a relationship, you just have to recall of these 4 graphs. So if you have a notebook, write them somewhere where it's clear so that you can be able to answer questions. Whenever you see these graphs, graph 101, you're going to deduce the relationship immediately by using some physics concept. After that, it's purely math. Look at these graphs, determine the graph that you need. So in this case, we're just going to draw something like this, and we'll be done, right? What did Cambridge expect us to do? The first mark came from you just drawing a curved line, a line with curves, right? Your A1 came for you drawing that line, but it's having a decreasing gradient. Okay, so those were the 2 main things that were just being considered. Let's move on. 4AI. By reference to the direction of propagation of energy, state what is meant by a transverse wave. Well, this is basically a wave that has its displacement. Okay, the displacement of particles is perpendicular to the direction of energy propagation. Perpendicular just means it forms 90 degrees. So if a wave is moving in a specific direction, and if the displacement of the particles that are on that wave is perpendicular, forming 90 degrees with the direction of energy propagation, you have formed a stationary wave. Sorry, you have formed a transverse wave. State the principle of superposition. Superposition, what does it say? It says that if waves meet or overlap at a point, right? Two waves are meeting. What are they going to do? They're going to wave. Hello? They're going to wave at each other as waves, right? No. Is when waves meet, the resultant displacement, right? When two or more waves, so basically when waves meet at a point, the resultant displacement, right, is the sum of the individual displacements, right? The sum of the individual displacements. When two waves meet at a point, the resulting displacement is equal to the sum of the individual displacements. So they don't reach each other, they just sort of add up. If one was moving with a specific displacement, the other wave is going to add up to that wave, and they're both going to be moving with a resultant displacement that is the algebraic sum of the individual displacements. B, circular water waves may be produced by a vibrating dipper that is at point P and point Q. So just a dipper just vibrates in the water. The wave from P alone have the same amplitude at point R as the waves from Q alone. Distance PR is 44, distance QR is 29. The dippers vibrate in phase with a period of 1.5 to produce wave of speed 4.0. Determine the wavelength. We're going to use the famous wave equation. V is equal to F lambda. So lambda will be equal to V divided by F. But guys, what do I know? I know that F is equal to 1 over my period T, which is equal to 1 over 1.5. Okay, so 1 over 1.5, that's going to be sort of my my frequency. And then for me to find my V, therefore my V will just be equal to, my lambda will be equal to 4.0 divided by 1 over 1.5, and that's just going to give me 6 centimeters. So it means that my wavelength, the wavelength of the waves, is actually going to be 6. So it basically means this wavelength lambda is just going to be 6 centimeters. I hope that makes sense, right? So we don't want to get lost. We've just been asked to find the wavelength of the waves, and I've asked myself, what information am I given? I'm given the period that can help me find the frequency. I'm given the speed that can help me find the lambda by using a wave equation. Don't get confused just yet, right? By reference to the distance PR and QR, explain why the particles are at rest at point R. Okay, so it's an explanation question and you're getting 3 marks. So you need to be very, very, very elaborate on this, right? Okay, so the distance PR is actually 44 centimeters. Are we in agreement? The distance QR is 29 centimeters. Okay, we need to find something that is known as the path difference. Right? The path difference is very simple. If you have a friend and you're going to the shops, the friend moves from one point, right? Let's say from their home A, and then you are moving from home B. Then you want to reach the shops, but your friend's path to reach the shops is 2 meters, 20 meters. Your path to reach the shops to your home is 60 meters. Your path difference is basically the difference in your paths, right? 60 minus 20 is 40 meters. That's basically the path difference. So if you have 2 waves coming from 2 specific points, reaching one specific point, path difference is basically the differences in the path that those waves have taken. So in this case, the differences in the path would just be 44 subtract 29. So 44 subtract 29 is basically going to be equal to, okay, 44 subtract 29, 15, right? 15 centimeters. Don't get lost, guys. Right, so we have two rules. We have two kinds of interference. Interference just means the effect that we see when waves meet at a point. Okay, we have two kinds of interference. Number one, we have what we call constructive interference. Don't get lost, guys. Interference. Okay, and I'm going to explain how that works. So we have constructive interference, and then number two, we have destructive interference. Okay, one is sort of an interference that's constructive, helps each other, and then the other interference is destructive. Okay, so the fancy term, right, what this just basically means is that constructive, the two waves add up, and then the resulting displacement is much greater, right? So it's going to be much greater, and this happens when the path difference is some product of the wavelength lambda, right? Some product. So in this case, our wavelength was 6, right? So if I had 24 as my path difference, 24 divided by 6, I'll get 4. So 4 lambda, right? 4 times lambda is actually my path difference. And whenever that happens, it means that you have constructive interference. Okay? And whenever you have n plus half lambda, right? It can be 3.5 lambda, half lambda, 4.5 lambda, 5.5 lambda. You have destructive interference. They're gonna meet, but then they're gonna cancel each other out. So it means that probably at that point they are differing. They have a path difference. They're differing by half, some half of wavelength. So it means that if you have probably a crest, it's gonna meet probably with a trough. Then they'll cancel out. Then they're gonna be at rest. But if they're differing by 1 lambda, it probably means it's the same wave. Right? If it's a wave like this, it's another wave, just they're differing by, by lambda, right? They're just differing by lambda. So it's the exact same wave, but just, differing by lambda or some multiple of lambda, but they're still gonna meet constructively. But if they're differing by half lambda, it means they're out of phase now. And then if they're sort of doing that, so if they're meeting with n plus half lambda, it probably means that when they're now going to meet, they're going to cancel each other out. So we have 15 centimeters. So if I divide 15 by 6, right? 15 divided by 6, I'm going to get 2.5. Okay, I'm going to get 2.5 of lambda. So remember, because I have this fraction of lambda, the path difference between them is 2.5 lambda. It categorizes under destructive interference. So it means that when they meet, they're going to destroy each other, and then after they destroy each other, they're going to have they're going to be at rest, essentially. So those are the 3 points that you need to find. Look at the path difference. If the path difference is n lambda, some multiple of lambda is going to be constructive. If it's n plus half lambda, it's going to be destructive. Those are the 2 scenarios that you need to consider. Why? Because if it's n times some multiple of lambda, they're still going to meet. If a crest and a crest are going to meet, then it's going to be much bigger. But if it's some lambda, it means that they're differing by sort of a small phase, and then when they're going to meet sort of at that point, but they're going to cancel each other out. One crest might meet with the next trough. They're sort of just disturbed in a way by half lambda, right? So that's basically how you need to think about. So whenever you see this question that asks you to explain where particles are at rest, those are the 3 points that you need to consider. So you first start by saying your path difference, right, is equivalent to 44 minus 29 divided by 6, which is just essentially 2.5 lambda, right? And then the second point is you're just going to say that the waves have a path difference of 2.5 lambda, because that's basically the path difference that's going to be existing. Right? And then so it's going to be destructive. So destructive interference occurs and your particles would be at rest. So that's essentially what you have to think about. 3 points: find the path difference, determine, since they have a path difference of n plus half lambda, right? Since they have a path difference of n plus half lambda, it probably means that destructive interference is going to be occurring. So those are some of the things that you just need to be thinking about. Find the path difference, then that path difference will sort of guide you in sort of figuring out what is going to happen. Is it destructive or is it constructive? Okay, I hope that sort of makes sense. Part C: a wave is produced on the surface of a liquid at one particular time. The variation of the vertical displacement y with the distance x is shown. So we're given this graph. The wave has intensity I1 at a distance x is equals to 2, I2 at a distance x is equals to 10. Determine the ratio of intensity I2 as well as intensity I1. So what do I know? What do I know, guys? I know that intensity is directly proportional to amplitude squared. So it means that I would just be equal to k times a squared. That's what you should know. If you're given a specific amplitude, your intensity will be directly proportional to that amplitude squared. Make sense? So it means that for me to find intensity I2, it will just be equal to k a2 squared. For me to find intensity 1, it will be just k a1 squared. These are constants, they cancel each other out, so you just be left with a2 squared divided by a1 squared. What is the first amplitude? The first amplitude is at a distance of 2.0. So go with that distance, go at 2.0. What is the amplitude that you have? If you look at here, this is 0.9. The next one is at 10. At 10 is here. If you look at that, that is 0.6. So what you're just doing is you're just saying 0.6 squared a2 is 0.60 squared divided by a1 0.90 squared. So you're essentially gonna get 0.44. 0.44. Okay, state the phase difference with its unit between the oscillations of particles at distance x is equals to 3 and x is equals to 4.0. For phase difference, we know that this is how much two particles are out of phase with each other, or how much they differ in having the same displacement at the same time. But basically, phase difference is equal to 360 or 2 pi times x divided by lambda, where x is just the difference between distances between those two things. So in this case is 360. The difference is 4 minus 3, which is 1 over, and then if you go on a graph, our value of lambda is, you pick the high point. Here we have 2. You pick another crest. Here we have 6. 4 minus 6 minus 2 is basically 4. So your wavelength will be 4. So here you have 4. So a quarter of 360 is basically 90 degrees. Right? So you have 90 degrees. So it means that particles oscillating at x is equals to 3, which is here, and x is equals to 4, are differing by 90 degrees. So it means that they're sort of having a phase difference. They're out of phase by 90 degrees, right? Very important for you to be thinking of that. 5AI. State what is meant by electric current. Well, current is basically the flow of charge carriers. Right? So basically current is the rate of flow of charge carriers. right? Which is the flow of charge carriers, right? These charges will be flowing. How much are they following? Define electric potential difference. Potential difference. Okay, so potential difference is basically the work done. The work done or the energy transformed, right, per unit charge, right, or the work done or the energy transformed from electrical, so it's going from electrical to other forms per unit charge, right, in a second. So what is work or the energy transformed from electrical? It goes from electricity, it can be light, it can go to light, it can go to heat, per unit charge in electric circuit. That is basically electric potential difference. B, a power supply of EMF 8.7, right? So this power supply has an EMF of 8.7 and the negligible internal resistance is connected by two identical wires, wire 1, wire 2, to 3 filament lamps. So a filament lamp 1, filament 2, filament 3, and the power provides a current of 0.30. The filament lamp are identical and the IV characteristics for one of the filament lamp is as shown. So we just want to show that the resistance of each connecting wire is 2.0. Very, very important. Okay, so from the graph, the PD across each lamp will be equal to, let's go to 0.30. Our I is 0.30, like here. So if you're gonna go like so, we're gonna reach at this point, and then if you're going to go down like so, this is 2.1, 2.2, 2.3, 2.4, that's 2.5. So it means that one filament lamp, if it is exposed to a current of 0.3, takes away, converts to light 2.5 volts. Okay, but we have 3 lamps, right? Essentially we have 3 lamps, so it means that across all 3 lamps our PD will be 2.5 by 3, which will just be 7.5 volts. So it means that the PD that will go in the resistors, so it means that the PD that will go in the connecting wire, right? So PD across the wire, right? We've been asked for each, pay particular attention to key terms, guys. We've been told that each connecting wire, we have 2 wires, so it means that whatever we do, we divide by 2, right? So we started off with a power of 8.7, so we're just going to say 8.7 minus 7.5 divided by 2. So 8.7 minus 7.5 divided by 2. So this is going to give you, right? So this is going to give me 0.6 volts, right? So I can safely say, but I know that V is equal to I. That my value of R will just be equal to V divided by I. My V here is 0.6. My I is 0.3. Then that's going to be 2 ohms. Very important for you to be thinking of that. And then you've been told the resistivity of metal of the connecting wire does not vary with temperature. Sketch the IV characteristics of one of the connecting wires. You should know that for a connecting wire, basically for a connecting wire, it is a straight line because it's an ohmic conductor. It is a straight line that passes through the origin. Okay, because if you know the variation of resistance in a wire, you can just be able to sketch the IV characteristics. They just want you to sketch the IV characteristics, right? So we know that I'm supposed to have a straight line, Okay, I'm supposed to have the straight line that passes through the origin. That's my first requirement, right? And then number 2, I can probably find its gradient, right? Because I know the gradient of this is just the change in I over the change in V. But I already have R, which is the change in V divided by the change in I, which is 2. So it means that my gradient would just be flipping this, right? Which would just be 1 over 2 with the gradient 0.5. So I need a line that is gradient 0.5, and I need a line that passes through the origin. So what do we do? What we do is simple. Our line must pass through, must have a gradient of half, right? So it means that if we have 0.20 here, what do we need for us to get a gradient of 0.5? Well, okay, or you can think about this saying that if we have 0.10 over here, for me to get a gradient of 0.5, it essentially has to pass over, right, 0. Right, essentially has to pass over 0.2. Okay, so it means that if I have 0.10 here, I'm going to have 0.1, 0.2 somewhere over here. If I have 0.20, for me to get 0.5, it must pass through what? Because I have 0.20, right? For me to get a gradient of 0.5 as a result, what specific thing do I need? Well, it essentially has to pass 0.4, right? So it's 1, 2, 3, 4. Okay, if you have 0.30, if you divide that by 0.5, you should pass with 0.6, right? So it's 1, 2, 3, 4, 5, 6. Like so. If you have 0.4, if you divide that by 0.5, you get 0.8. So 0.8 should be somewhere here. So this should be your line, right? With the gradient 0.5 being a straight line that passes through the origin. So it's going to start here at your origin, then it's going to go and be like so, right? That's your straight line that passes through the origin. So you just had to think about that when you were doing these calculations. You need a straight line that passes through the origin that is a gradient of 0.5. right? Why 0.5? Because since the resistance is 2, I over V is 1 over the resistance, so it must be 0.5. The power loss in one of the connecting wires. So we know that power is essentially VI, right? But V is equal to IR. Therefore, your power will be equal to I squared R. Right? Why is power equal to VI? Well, you might ask, power, we know that is the work done per unit time, but V, electric potential difference, is the work done per unit charge. So work done will be equal to V times Q. So power will be equal to VQ divided by T. But Q is equal to IT, therefore Q over T will be equal to I. So your power will be equal to VI, right? So V times I, right? It's essentially. So that's why power is just, equivalent to VI. So that's something that, you must just know. But essentially, we can substitute with IR and get power is equals to I squared R. The value of I that passes through this, as you have been told, is 0.30 squared. My resistance is 2. So it means that my power that I lose is 0.18. Right? Part V. Some data for the connecting wires are given below. Cross-sectional area, resistivity, and number density. Calculate the length of one of the wires. So we want to find the length. What do I know? I know that resistance is equal to rho, resistivity, times L divided by A. So my length will be equal to my resistance times A divided by my resistivity. My resistance for a wire is 2. My area is 0.40 times 10 to the power of negative 3, which is a milli. Okay. resistivity, which is 1.7 times 10 to the power of negative 8. You punch that into your calculator, and then you basically get 47 meters. So the wire is 47 meters long. That's pretty long. 2, we know that I is equal to AN VQ, right? From the famous equation for current in a current carrying conductor. So from this, my V will be equal to my I divided by my A times my N times my Q. My I is 0.30. My A is 0.40 times 10 to the power of negative 3 R squared. My N, if you look at here, it's 8.5 times 10 to the power of 28 times 10 to the power of 28. My Q is 1.6 times 10 to the power of negative 19. So it means that my drift velocity will just be 5.5147 times 10 to the power of negative 5. So I will essentially get 5.5 times 10 to the power of negative 5 as my drift speed. Okay, very important for you to be thinking of these things, guys, when you're in your exam. A neutron decays by emitting a beta negative particle. Complete the equation below. So basically, when it decays, it forms a proton, right? And we know that a proton has a proton number of 1 because it's one proton, and a nucleon number of 1 because it's one nucleon. A beta negative particle has a nucleon number of 0 because it's not a nucleon, and a mass number of negative 1 because it's just like, you know, a beta negative particle, so it needs to have a negative 1. And then electron neutrino, mass of 0, and then it's neither, you know, a nucleon or anything like that, so it's going to have 0. So we've conserved everything. 1 minus 1 is 0. 0 plus 0 is 0. Yes. 1 plus 0 plus 0. Yes. So the name of the particle represented by the symbol of this is known as an electron anti-neutrino. So the name of the class or group that includes B negative and B, these are basically leptons, right? Why leptons? Because they do not experience nuclear force. So they have to be leptons because they do not experience any nuclear force whatsoever. State the quark nature of the neutron. So essentially, a neutron consists of an up quark, a down quark, and a down quark. So the quark composition of a nucleus is basically something like this. So if we've been asked to state the structure, the quark structure of the nucleus, that's basically going to be up. Okay, we go up, we go down, we go down. So it's essentially up, down, down. State the change to the quark structure when the neutron decays. So when a neutron decays, since we had a neutron that went to a proton, so a neutron, we know that this is up, down, down, right, like so, and then it went to a proton. A proton is an up, up, down, like so. So as you can see, what this basically means is that a down quark, right, a down quark was changed to an up quark for this to be possible. Okay, so what we're just saying, the quark composition is that a down quark changes to an up quark. So a down quark will change to an up quark, or the entire quark composition will change from being an up, down, down to being an up, up, down. So basically, that's it, right? So this was how you're supposed to think of this question, solving these questions in depth. And here's my trick, here's my tip for how you can tackle A-level physics questions. What you're going to do, I would highly encourage that you have a perfectly nice notebook that consists of notes from syllabus objectives that you'll be covering, as well as from the test book that you are given. Then after that is done, you can therefore be able to sort of write your notes from question papers. So as you'll be going through these question papers, these are very, very important notes that you need to have. For example, the question that I gave you about graphs, they're very important thing that you can be able to answer. Because if you didn't know that that existed, you probably wouldn't have been able to answer that question. And my guess is, well, you haven't exactly been taught how to answer such specific questions in your class, unless you probably have a physics YouTube or something like that. But you know, these are some of the things that are not taught in class, but these are tricks that you're supposed to have as a student. That whenever you make a relationship, you can therefore just relate to a specific graph that you know. But these are specific things that you might not even be taught in the normal classroom. So it's up to you, yes, to listen to what you're taught, or for you to research from the textbook and all of that. But if you don't do past papers, and if you don't do a lot of them, then you'll be in serious trouble. And my advice is, don't just rely on worksheets that give you question papers from, I don't know, 2016. Do all of them, even question papers from 2000s, right? They help you gain better understanding and see what concepts are unclear. And some of these questions are actually repeated. So you might find a similar question in 2002 repeated with different wording in 2028. Repeated it with different wording in 2022. So it's very important for you to be thinking of that as you be answering your physics paper. I really hope that this was helpful. And if you do like my content, please like and subscribe. And I'll see you guys in the next.